In the previous video, we have discussed the step-by-step process of finding the allowable bending stress for a steel beam that has a compact section that fall in the category of case 1 and case number 2. For this video, we will focus more on case number 3, and that is when the unbraced length LB exceeds the value of LC and LU. Okay, so we'll use the same problem we used in the previous video. And we already answered item number 1 and item number 2. And for this demonstration, we will answer item number 3 and item number 4. Okay, let us answer item number 3. We are to compute for the allowable bending stress if the beam has a simple span of 6 meters. Again, step number 1, we have to check if the given section is a compact section. But we already knew this because we used this problem in the previous video. So we'll just speed up everything. So therefore, the flanges are compact and also the web is compact. Therefore, we have a compact section. Step number 2, determine what case. So to do that, we just need to find first the value of LB and we compare it to the value of LU and LC. So for this case, the value of LB, since the problem specifically stated that the beam has no lateral support, then our LB will be equal to the span of the beam itself, which is equal to 6 meters. So the value of LB is 6,000 mm. We just converted the value of 6 meters to mm. Okay, then to solve for the value of LC and LU, we use these two quantities. Whichever is the lower value, that would be our value for LC, and the higher value will be our value for LU. Okay, solving for the first one, we have 200 multiplied by BF is equal to 292.35 mm over the square root of Fy, which is equal to 248 megapascal. Then the result is equal to 3,712.849 mm. In the second function, we have 137,900 over Fy, which is equals to 248, and the total depth, which is equals to 840.74 mm over the width of the flange multiplied by the thickness of the flange, and that is 292.35 times 21.72, and the result is 4,199.657 mm. Since this has the lower value, this would be our value for LC. And this one right here is the value for LU. This one is the value for LB. Next, we will compare LC and LU to the value of LB. Obviously, LB exceeds both LC and LU. Therefore, we are in case number 3. Now remember that the value of the allowable bending stress for case number 1 is 0.66 Fy, and for case number 2, Fb is equals to 0.60 Fy, a little bit lower than the value of case number 1. Similarly, for case number 3, we are expecting a lower value of the allowable bending stress. It should be lower than 0.60 Fy. Computation for the allowable bending stress for case number 3 is a little bit complicated because case number 3 is further subdivided into 2 cases. And in this tutorial, we will name them as case number 3.A and case number 3.B. For case number 3.A, we have this criteria. And for case number 3.B, we have this one. You are familiar with Fy. Fy is the yield strength of the material used for the beam and is usually given in the problem. L is the span of the beam and also usually given in the problem. And L over RT is what we call the slenderness ratio of the beam. What I want to emphasize in this tutorial is finding for the value of CB and RT. So what is CB and RT? CB can be computed using this formula, and it should not be more than 2.3. In the formula, M1 is the smaller bending moment taken at the end of its unbraced length taken about the strong axis. Similarly, M2 is the larger bending moment, also taken at the end of its embraced length about the strong axis. So we can call M1 over M2 as the ratio of end moments. Let us consider this beam. Suppose this is subjected to a clockwise moment, a positive moment at its end, and another clockwise moment on the other end. The beam's elastic curve will look like this. We have a double curvature. Similarly, if we take another beam and it is subjected to a negative moment, a counterclockwise moment on both ends, then its elastic curve will also have a double curvature. For this case, the ratio of end moments is positive. But if the beam is subjected to end moments that are oppositely directed like this one, we have a clockwise moment on this end and a counterclockwise moment on the other end, then the elastic curve will have a single curvature. Same situation if we have a negative moment on the left end and a positive moment on the other end or the right end, the elastic curve will also have a single curvature. And for this case, the ratio of end moments will have a negative sign. Other values for CB includes when the bending moment at any point within a braced length is larger than the moment at both ends of its length, then the value of CB is equals to 1.0. This includes simply supported beams and cantilever beam. So that's how you compute for the value of CB. Now let's talk about RT. RT is defined as the radius of gyration of the section comprising the compression flange plus one-third of the compression web area taken about an axis in the plane of the web. So based on the definition of RT, it is a radius of gyration and the formula is equal to the square root of moment of inertia all over area. So if you want to find for the radius of gyration of this section, we'll just solve for its moment of inertia and its area. Then we use the formula. But I want to emphasize that RT is not the radius of gyration of the section. It's not as simple as that because in the definition of RT, it is the radius of gyration in the section comprising the compression flange plus one-third of the compression web area only, as opposed to the radius of gyration wherein you have to consider the total area. To do this, we'll draw the neutral axis. And on the upper portion, we have the compression side, and on the lower portion, we have the tension side. On the compression side, we have the compression flange and the compression web. But since we are only considering one-third of the compression web, it would be this area, where this distance is one-third of this distance. The highlighted portion of the section is the one we are going to use to find the value of RT. But that's not all, because according to the definition, RT is taken about an axis on the plane of the web. Example of that axis is this one. So to solve for RT, we need to rotate the section, and to solve for RT, we'll be using the formula for the radius of gyration, but considering only this portion of the section. So this is the formula for RT. So that's how you solve for CB and RT. Now let's come to the computation of the allowable bending stress for case 3A and case 3B. For case 3.A, we have this formula, and for case 3.B, we have this one. But before you give your final answer, make sure that these values are not lesser than this one. You may consider this as the minimum value of the allowable bending stress for case number 3. If in case the value of FB is lower than the minimum value, for example, if the value of this one is lower than the value of this one, then you have to consider this one. Kung mas guti ang value hini, kontrahan niya di, adit imo answer. And also, you have to remember that our value for FB should not be lower than 0.60 Fy. That is for case number 3. We also have to check for it for our solution. You may think of it as the maximum value of the allowable bending stress for case number 3. Now let's go back to our problem. So we already know that we are in case number 3, but we still need to know if it's case number 3.A or 3.B. And we need to find for the value of these three quantities. To do this, we will need the value of RT. From the problem, these are the given, and we will be solving for the value of RT. So we have the neutral axis here, and the clear distance between flanges is 797.30 mm. So from the neutral axis to one face of the flange, the distance is 398.65. And we only be considering this portion of the beam. And this distance right here, the value of x, is only 1/3 of this distance. And that is equal to 132.88. And one more thing, we have to put it this way. Then to solve for RT, we will use this formula and we will divide the section into two regular shapes. We have A1 and A2. Solving for the moment of inertia, we will use this formula. Now, take note, we can only use this formula if and only if the neutral axis of all the area in a composite section lie on the same plane. So for A1, the neutral axis is this one, and for A2, the neutral axis is this one. So that means that the neutral axis for all the areas in this composite section all lie on the same plane, and that is this one. Okay, so we can use this formula. We have for A1, we have 21.72 times 292.35 cube over 12. And for A2, we have 132.88 times 14.73 cube over 12. And the result is 45.26 times 10 raised to 6 mm raised to 4. Solving for the area, we only need to sum all the areas, A1 plus A2. For A1, we have 292.35 times 21.72. For A2, we have 14.73 multiplied by 132.88. And the result is 8,307.16. And we'll use this result in the formula. And the answer for RT is 73.81. And that's the value for RT. So solving for L over RT, L is 6,000 and RT is 73.81. The result is 81.21. That's the value of L over RT. And CB is equals to 1.0 since it's a simply supported beam. And the value of this quantity is equal to 53.25. And this one, that is equal to 119.08. Now, L over RT is somewhere in between this one and this one. Therefore, we are in case number 3. We'll be using the value of L over RT, RT and CB. So, to solve for the value of FB, we'll be using this formula because we are in case number 3.8. So we'll use that formula and we already have the value of everything here. We have the value of Fy and that is 248 megapascal. We have L right here, 6 meters or 6,000 mm. And the RT 73.81. CB also is here, 1.0. Direct substitution na lang siya. Okay, so the result for FB using this formula is 126.81 megapascal. But it's not yet the final answer because you still need to check whether if it is lower than this value. So you still have to solve for this one. And we need the value of the depth, the width of the flange, and the thickness of the flange. So right here we have the depth, the thickness of the flange, and the width of the flange. Then we use that value to solve for this one. FB therefore is equal to 104.15. Since 104.15 is lower than this one, we will use this one because the value of FB, this one, should not be lower than the value of this one, which is correct. It is not lower than this one. So we'll use this value. But before you give your final answer, you also need to check this one because your FB for case number 3, it should not be lower than 0.60 Fy. And 0.60 Fy is equals to 148.8 megapascal. Since it is not larger than 148.8 megapascal, then this is your final answer. 126.81 megapascal. And that is your answer for item number 3.